Welcome to this YieldOptiX tutorial focusing on setting up test limits and yield simulations. Functions applicable at various stages of the product lifecycle and particularly critical during new product introduction. This tutorial will showcase various scenarios, including limit adjustments based on input from the project team, increased manufacturing variability, fab process tuning, changes in test settings, or efforts aimed at improving quality and reliability screening. Let's begin by examining real-world test data logs for a new product by generating a results summary table, which is available with a single click from the Test Explorer. Sorting this data by the count of out-of-spec results brings tests most critical for yield to the top of the Pareto list. All of the tests at the top show unacceptable CPK and PPK values, along with a high number of fails, indicating a critical mismatch between the distribution and the actual limits. One can simply select these tests in the table to further review the results. These tests are then immediately filtered into the main test list within Test Explorer. One can quickly get a first impression of the data distribution using the Quick Plots function by selecting a normal quantile type plot and basic parameter maps from the available plotting options. Upon clicking OK, the report is generated immediately. In situations where product results respond to increased process variability or changes in test conditions, adapting these limits may be plausible. Test limits can be accessed easily through the Manage Spec Limits button available in Test Explorer. Clicking this button opens a window that lists the tests, current limits, units, and multiple options, greatly simplifying the process of limit adaptation. Even for thousands of measurements, by utilizing calculations based on a target process capability index. Initially, let's adjust the limits for selected tests by setting a CPK target of 2 and keep the default sub-options checked, such as displaying calculated limits as reference lines, rescaling the y-axis to clearly show new limits, creating a new spec limit table, and enabling the Fill the Limit table with New Values option. This function will automatically populate the limit values within the Manage Spec window. Also, let's keep the Use PPK over CPK option active, as it utilizes the overall sigma from the entire dataset. One can disable the Use Median instead of Mean checkbox, as the distribution for the selected tests do not significantly deviate from normal. After adjusting these settings, a single click on Calculate Statistical Limits generates a table comparing actual and calculated limits. In this table, the narrower limit between the actual and the calculated limits for a given test is highlighted in yellow. With the Show Limits as Reference Lines option checked, one can now visually inspect these limits on the charts, making them easy to review before acceptance. Let's again use normal quantile plots from the Quick Plots function. The calculated limits appear as red reference lines with labels indicating the target capability index value. This strategy is well suited for scenarios where AT test conditions or fab processes have changed, leading to distribution shifts or increased spread. It can also be appropriate in AT-specific environments where direct validation of certain parameters is limited and statistical techniques for defining limits offer a practical alternative. Once the refined limits are reviewed, they need to be confirmed using the Save to Column Properties button so they become active in the analyzed data set. A single click on Remove Statistical Limit Lines clears future plots from red dashed lines, ensuring they are not duplicated alongside the accepted limits. After adapting limits to new processes or test case setups, let's regenerate the statistical summary table. As observed, all spec counts drop to 0, with a PPK at the exact value of 2. Returning to the Manage Spec Limits window, the original limits from the STDF file can always be reset with a single click on Restore Limits to Initial, so the STDF file doesn't need to be reloaded in case of an unwanted result or mistake. The Manage Spec window automatically closes, and once reopened, the limits are back to their initial state. Now let's consider another variant, where the observed fails reflect increased and accepted process variability. An additional margin between the upper and lower limits is needed to accommodate material not included in the analysis or used in defining the initial limit set. YieldOptiX supports this scenario through the option Take Actual Limit when looser. As before, one can set the target CPK value of 2 and keep the same checkbox options enabled. With a single button click, 2 additional columns appear in the table compared to the previous case, showing the calculated upper and lower limits for the given PPK target value. The Refined Limits column is then populated with whichever value, actual or calculated, is looser for each test. Again, these preset limits can be investigated using normal quantile plots from the Quick Plots option. In some plots, the red lines overlap with the actual limits, indicating that those limits remain unchanged because they are already more relaxed than the calculated ones. Once the limit set is ready and the refined limits have been tested and reviewed, they can be saved to the table with a single click on the Save to Column Properties button. One can then confirm that reference lines are no longer needed by clicking Remove Statistical Limit Lines. After the limits are accepted, the statistical table in Test Explorer can be used again to verify the results. Out-of-spec values drop to 0, and the limits are updated with a consistent PPK value of 2, including cases where one of the original, more relaxed limits was retained. In all cases, the calculated limits tend to be difficult to read, compare, or interpret, as they are generated with maximum numerical precision to meet the exact target capability measure. To resolve this and produce limits that are more practical and human-readable, the adaptive limits rounding option can be used. This option leverages a machine learning algorithm developed by SilTest, which determines the most appropriate rounding based on a user-defined absolute deviation threshold for capability metrics. Deviation is minimized within the given threshold to ensure meaningful precision without compromising the statistical goal. As with earlier steps, it is possible to select the use of median instead of mean, and PPK instead of CPK. In this case, let's leave the default allowed shift of no more than 0.1 for both CPK and CP. By clicking the Adaptive Limit Rounding button, the calculated values are transformed into clean, human-readable limits that are easier to interpret and compare. Once these limits are reviewed and accepted, they can be saved directly to Column Properties. Using the Save to Tall Limits table option, a complete and structured limit set can also be exported and shared across the project or engineering teams in a consistent and readable format. Again, the statistical table can be used to confirm that all spec counts are 0 and that PPK values remain consistent. The updated limits can also be seen in the normal quantile plots, confirming that the refined limits accommodate increased variability while minimizing the risk of overkill. This process can be applied to thousands of measurements at once through the Manage Spec Limits interface. Let's now look at another use case, setting limits from the beginning when a predefined table is provided by the design team. This process is also streamlined through the Manage Spec Limits option. Looking at the limit table, the test names clearly indicate that these are trim tests. To begin, let's first examine the measurement results for the trim offset of high-side switches, which can be easily isolated from other tests using the dynamic filtering lists. For a quick overview of the data distribution, the parallel box plot charts from the Quick Plots function can be used. This view provides full measurement context, with test names along the x-axis and corresponding results on the y-axis. Now, let's open the Manage Spec Limits window. Uploading the associated limits from external tables is straightforward using the Load from Limits Table function, followed by selecting the appropriate dataset. Once loaded, the limits automatically populate the view and can be confirmed by clicking the Save to Column Properties button. Moving back to the chart, the applied limits are now visible. The bottom line represents the lower and the top line higher limit. The middle line indicates the calculated target value. As before, one can quickly verify the failing test Pareto by opening the statistical summary table from the Test Explorer, confirming that the out-of-spec count is 0 and the CPK and PPK values are very high. However, upon reviewing the chart, it becomes noticeable that some tested parts clearly stand apart from the main distribution, showing a steady readout around 0 across multiple trim codes. Unfortunately, the currently applied limit set accepts these questionable results as passing. These results appear highly suspicious, and due to potential reliability and quality risks, such outliers should ideally be screened out. To make these questionable parts more clearly visible, one can utilize the Graph Builder option, changing from box plots to point plots and enabling uniform jitter. Immediately, the outlying behavior of several parts becomes more pronounced. To define proper limits across the entire trim sweep, ensuring suspicious points are filtered out, one can return to the Manage Spec Limits window. This time, let's set a higher target CPK of 3, keeping most options enabled, but disable the Tall Limits Table function, enable direct population of the view with calculated limits, and apply adaptive limits rounding to directly produce meaningful numeric data formats. After clicking Calculate Statistical Limits, one can see from the chart that the newly calculated limits correctly identify and screen out the suspected parts and would classify them as failures. However, it's also visible that the calculated limits now violate the provided design constraints for some trim values. Returning to the Spec Manager window and selecting the Take Actual Limits when tighter option solves this issue by ensuring that newly proposed limits never extend beyond defined design constraints. Let's now clear the reference lines from the previous trial and click Calculate Statistical Limits again. The revised limits now clearly remain within the specified constraints, effectively screening out all previously identified suspected parts across multiple tests. To finalize these limits, let's confirm them in the Spec Manager window by clicking Save to Column Properties, and then clear the temporary trial lines to keep the charts clean. By generating this statistical summary table from the Test Explorer, one can verify the exact number of failed parts per switch and trim condition, simultaneously ensuring that desired PPK values are achieved. To simulate the overall yield impact of screening these defective parts, simply click on Find Failed Device for selected. This immediately displays the overall yield reduction resulting from the combined failing tests per part. One can see that 6 failing parts represent approximately 0.18% of the total yield, and these identified parts are clearly highlighted in the chart. This demonstration showcases the efficiency and precision of SilTest, effectively streamlining complex processes and ensuring optimal outcomes. Stay tuned for more innovative features from YieldOptiX, designed to simplify your workflows and enhance operational efficiency. Thanks for watching.